Hello everyone, I'm Bin Tian from Alibaba, and I just received my PhD degree in Nanjing University. Today I'm going to present Aquila, a practically usable verification system for production-scale programmable data plans. This is a joint work during my internship at Alibaba with my colleagues from Harvard University. As a prominent online service provider, Alibaba operates a global network infrastructure serving over 1 billion customers. As services today constantly evolving in size, it's becoming increasingly difficult for edge networks to handle the ever-growing traffic due to resource constraints. This promoted us to offload a group of network functions from servers to save CPU resources and get better performance. Recent advances in programmable networks have enabled us to implement network functions using P4 language. It gives us a cost-effective solution to greatly improve the performance of our edge networks in terms of both functionality and efficiency, as well as flexibility. Given these advantages, we have widely deployed programmable switches in our edge networks. With the increasing diversity of our services, the data plan programs are greatly increasing in complexity. Each program may consist of thousands of lines of P4 code and multiple pipelines, and each pipeline holds a number of network functions, such as NET, load balancer, and DDoS defense. The network functions across different pipelines are tangled with many packet paths, resulting in complex function chain within a single programmable switch. Therefore, it's a great challenge for developers to ensure the correctness of data plan programs. To prevent any possible data plan bugs, we need a practically usable verification system to rigorously verify the correctness of data plan programs. To make the verification system practically usable, a simple and powerful language is required to help developers read their intent in an easy way. The verifier should be able to verify production-scale data plan programs and give results within a tolerable time. When the verification task fails, the verifier should try to localize the bug, instead of just printing a counterexample on a trace. And last, the verifier should be confident to its verification result and try to avoid any false positives and false negatives. The above 4 points correspond to our 4 challenges. The first challenge is about the intent complexity. It's not easy to describe some intent accurately in a simple way. For example, see this intent. For each TCP packet, we shouldn't change its TCP header. It's very natural for us to understand it, but from a verifier's perspective, what's the definition of TCP packet? Is a packet with TCP header a TCP packet, or a specific header order is required? Here, of course, the second packet is not what we want, but it's not easy to tell this point to the verifier. If we follow existing work, we will have to write a lot of lines to express this point. It's very complex and also error-prone. It would be much better if we can express it in one line. The second challenge is about the scalability. Our production programs are composed of a layer 3 switch and a lot of network functions. It's not easy to verify such a big program efficiently. In addition, our production programs are mainly written by P416 instead of P414. In P414, the ingress logic and egress logic are combined to one logical pipeline and share one parser. But in P416, they're divided into 2 logical pipelines. Each pipeline has its own parser and deparser. Unfortunately, it's exactly the parser and deparser that contributes the major complexity to the verification. The next challenge is about bug localization. When the verification task fails, only printing a counterexample and a bug trace is not enough. In our production programs, the bug trace contains over 100 steps, and it's still very hard for developers to localize the bug. The last challenge is about the reliability of the verifier itself. A verifier can also have bugs, which may mask the program's bug. This kind of bug is really hard to find, because in this case, the verifier only tells you the verification is passed, without any other information such as a counterexample and traces. So a validation mechanism is required to make the verifier more reliable. To solve all above challenges, we built a production-scale data plan verification system. We designed a simple and powerful intent language to help developers describe the desired property. Next, we proposed a set of encoding algorithms to translate P4 programs into guarded command language and solved the scalability problem. Then, we reused the verifier to build a bug localization algorithm that analyzes the causality of the bug. And last, we use a cross-checking algorithm to validate the correctness of the verifier. Now, I will introduce the first part, the intent language. The key insights of intent language are summarized from our experience. For example, we noticed that most intent can be placed before a pipeline or after a pipeline, but seldom inside the pipeline. This gives us a chance to represent all intent as a single independent file, instead of adding annotations in P4 code. I will use an example to show how to write an intent file. An intent file is composed of 5 blocks. The program block describes how these pipelines are organized. For example, the green part means each packet should first execute the ingress part of pipeline A. If it's not dropped or redirected to CPU, execute the egress part. Here, pipeline A is defined in the pipeline block. This block describes the property of a pipeline, such as pipeline IDs and table entry snapshots. Next, we use the assumption block to describe preconditions, and use the assertion block to describe postconditions. These 2 blocks can be inserted into anywhere inside the program block. We provide high-level abstractions to help developers describe their assumptions and assertions in an easy way. Developers can write an intent program with this language and then start a verification task. The intent program is almost fully decoupled with the data plan programs, so we don't need to update the intent program even if the data plan program updates. Next, I will introduce how to make the data plan verifier fast and scalable. A P416 program is composed of 3 parts: the definition of packet headers and metadata, the parsers and deparsers, and the match action units. We use Dexter's classic method to verify a program, and we make no claim on the novelty of verification technology. Instead, our contribution is how to encode a P4 program to another program that can be efficiently verified. The key complexity of P416 verification comes from 3 aspects. The first one is the state machine language of packet parsers. Simply expanding the state machine into a verifiable program can lead to state explosion. The next problem is the extremely branchy table entries. Although we can merge some entries to reduce the complexity, not all of them can be simplified. The last problem is the connection of 2 pipelines. When there are more than 1 pipeline, we will have to encode this part, and the above complexity multiplies. In this talk, I will only introduce how we solve the first problem. Now, let's see the state explosion problem of packet parsers. Look here, there is a parser, and it's also a state machine. In each state, the parser extracts corresponding packet header and then transits to another state according to the field of the header it parsed. Look at this transition. It's not a typical branch structure because it has 2 parallel exits. That means we can express this with the if statement. A straightforward way is to expand a state machine into the tree, so that we can easily express the tree with the if statements, and then it's trivial to verify the program. However, We can see that in the bottom of the tree, two states are duplicated. It's okay for small programs, but not acceptable for large programs, because the tree can be very deep. In the worst case, there can be over 1,000 duplicates. Verifying such a malformed program requires a lot of memory and several days. To solve this problem, we proposed sequential encoding to reshape the state machine. Let's assume the parser is acyclic, so that each state can only be visited at most once. In addition, for any two states, they are either mutually exclusive or have a fixed order of execution. That means the acyclic parser can be regarded as a sequence of states. Each state can be visited once or not visited, depending on previous states in the sequence. For example, whether to visit TCP state depends on the protocol number from IPv4 or IPv6 state. Whether to visit the IPv4 state further depends on the Ethernet type from Ethernet state. Here is an example of sequential encoding. We use the following 4 steps to translate a state machine into a simple verifiable program without any code duplication. There are some details remained. The first one is about the external functions, such as how to avoid indexing the packet bit vector in parser's extract function. The second one is about how to handle the parser loops. In this talk, I will skip these details. You may find them in our paper. Next, I will talk about bug localization. In programmable data plan, a bug may appear anywhere. When a data plan bug directly leads to a wrong hardware behavior, a control plan bug may install buggy entries to hardware tables. Aquila can localize data plan bugs in both two cases. In this talk, I will only introduce how to localize a bug in data plan programs. Consider a bug in data plan program. We need 3 steps to localize it. First, we use the counter example to construct an execution trace that triggers the assertion. Next, we use a fast algorithm to find out suspicious statements in the trace. And finally, we use a verification-based slow algorithm to check the causality between the violated assertion and each suspicious statement. I will use an example to show how it works. Assume the buggy trace has been constructed, so we start from the violated assertion to analyze which variables can make the assertion invalid along the backward direction of the trace. Initially, we know variable v6 is suspicious because there's only one variable in the violated assertion. Then we go back. We find v6 is assigned by v4, so before the execution of a3, v4 is suspicious. Next, we find v4 is assigned by v4 itself and v2, so before the execution of a2, both v4 and v2 are suspicious. And finally, we find v4 is further assigned by v1, so before the execution of a1, both v1 and v2 are suspicious. Note that v1, v2, and v3 are not assigned by any other variables. That means the value of these variables are constrained by preconditions and is always correct. So we need to remove them from the suspicious list. Now we know, before the execution of a2, a3, and the assertion, the assignment to v4, v4, and v6 are probably wrong, respectively. Now we use the verifier again to precisely localize the buggy assignments. Let's see the structure of a data plan program. The graph shows all possible execution paths. Here the solid lines are the buggy trees. Recall that v4 is suspicious before the execution of a2. That means the assignment of v4 in a1 is probably wrong. To determine whether the assignment is really wrong or not, we need to check the causality between a1 and the assertion. A possible way is to verify if the violation of the assertion always implies the visit of A1. If it's not true, we know the bug comes from another action instead of A1. Similarly, we can check the causality for all suspects. Assume that we find V4 gets wrong just before the execution of A3. That means this assignment in A2 is wrong, so we successfully localize the bug. The last part of Aquila is the self-validation. We use a cross-checking algorithm to prevent buggy verification results. In this talk, I will skip this part. Please see more details in our paper. Now let's see how Aquila performs. We choose invalid header access as benchmark to evaluate Aquila's verifier, and record the time to find the first bug and find all bugs. Results show that multi-pipeline is a major overhead of verification, because with more than one pipeline, the verifier must encode the depassers and additional passers. Passer state is another overhead of verification. Here we can see that Aquila spends more time in verifying program 3. Although the number of states of program 3 is 3 times that of program 2, the lines of code is only 1/3. Now let's compare Aquila with existing work. From the results, we can see that without Aquila's encoding algorithm, it's almost impossible to verify multi-pipeline programs with complex parsers. Next, we use 3 programs with different scale to evaluate Aquila's bug localization algorithms. We injected 3 kinds of bugs, including wrong table entry, code missing, and code error. Results show that Aquila can localize all these bugs within several minutes and narrow down the suspects. Finally, I will use a real example to show how Aquila is used in Alibaba's P4 program verification. Here are the pipelines of a production-scale data plan program. Their 3 functions are implemented in switch ingress and switch egress, while custom functions such as load balancer are implemented in LB ingress and LB egress. When the packet enters switch ingress, it will be forwarded to LB egress, then recirculated to LB ingress, and finally forwarded to switch egress and leave the switch. One day, our developers need to decapsulate VXLAN packets in LB egress and then route the decapsulate packets. But routing tables are placed in switch ingress. There is no hardware resource to place another routing table in LB ingress. To solve this problem, our developers decide to swap the switch ingress with LB ingress. This changes the dependencies between 2 pipelines. For example, the net function is originally placed in LB ingress, while the ACL function is placed in switch ingress. After the swapping, the ACL table will match the netted addresses instead of the original addresses. We use Aquila to verify whether the semantic of each function are equivalent before and after the swapping, which proves that Aquila is practically usable in verifying production-scale data plan programs. In conclusion, Aquila is the first practically usable verification system for production-scale programmable data plans, and we summarize our experience from Aquila as follows. First, verification shouldn't be a burden of developers. It's necessary to minimize manual intervention and don't disturb the normal process of the development. Second, time consumption determines the scenario and frequency of the use of a verifier. For example, with less than 20 minutes, developers will be very eager to use it in daily development. Next, when the verifier finds the bug, developers need detailed information to localize and then fix the bug. Otherwise, they would be very confused and spend a lot of time in understanding what's wrong. And last, a verifier should be able to find its own bugs proactively. Otherwise, it may be blind to some bugs in the verified programs and is really dangerous to network reliability. Finally, there are some open problems. For example, how to verify the distributed data plan with heterogeneous ACs, and whether we can use an interactive way to precisely localize the bug and even fix the bug. These problems are quite hard to solve, and solving these problems will definitely make data plan verifier much more practical. This is the end of my talk. Thanks for listening.